Somewhere out there, two galaxies are falling into each other in slow motion, and at the heart of each one is a black hole millions or billions of times heavier than our sun. When those two monsters finally touch, the collision will briefly outshine every star in the observable universe combined, not in light, but in something stranger. It happens in spacetime itself, and it ends with one warped, scarred black hole rocketing away from the wreckage at speeds that can outrun its own galaxy. Almost every large galaxy has one of these giants sitting at its center, a supermassive black hole ranging from a few million to tens of billions of times the mass of the sun. Galaxies are not static. They collide and merge constantly over cosmic time, pulled together by gravity across millions of light years. Our own Milky Way is on a collision course with Andromeda right now, and simulations show the two galaxies will start colliding in about 4.3 billion years and fully merge within roughly 10 billion years. When two galaxies merge, their central black holes do not collide immediately. Instead, they sink toward the new combined center through a process called dynamical friction, plowing through stars and gas like two cannonballs dragging through sand. This drags them from a separation of thousands of light years down to just a few light years apart, and at that point, they officially become a bound binary, two black holes locked in orbit around each other. Here is where the story gets stuck. Once the black holes are about a parsec apart, roughly 3 light years, the stars and gas that were dragging them together start to run out. Simulations show that at this distance, gravitational waves alone are far too weak to finish the job, and the binary can stall for longer than the current age of the universe. Astrophysicists call this the final parsec problem, and it has been one of the most stubborn puzzles in black hole physics for decades. So how do real binaries actually escape this trap? One leading idea is that clumps of gas falling into the galactic center feed a disk around the pair, and torques from that disk siphon away just enough orbital energy to bridge the gap. Another proposal, published in Physical Review Letters in 2024, suggests dark matter itself is the missing ingredient, arguing that a dense, self-interacting dark matter core acts as a reservoir that soaks up the binary's energy and pulls the black holes past the final parsec. Either way, once the black holes get close enough, gravity itself takes over completely. Once the separation shrinks to something like 1/100th of a parsec, gravitational waves stop being a side effect and become the dominant force in the system. Every orbit, the black holes bend spacetime so violently that ripples radiate outward, carrying away orbital energy the same way a spinning skater loses momentum by throwing weights outward. The tighter the orbit gets, the faster the black holes radiate, and the faster they radiate, the tighter the orbit gets. It is a runaway feedback loop, and once it starts, there is no stopping it. This entire process, from wide binary to final plunge, is called the inspiral, and gravitational wave physicists split the whole collision into 3 acts. First, the inspiral, where the black holes circle each other for the long haul, slowly at first, and then faster than sound, faster than light itself would take to cross their own event horizons. In the final moments before contact, each black hole can be moving at a meaningful fraction of the speed of light, and their combined gravity twists the space around them into something almost unrecognizable. Then comes Act 2, the merger itself, and it happens shockingly fast. The two event horizons stretch, touch, and fuse into a single distorted horizon shaped like a peanut, all within a span of milliseconds for stellar mass black holes, or minutes to hours for their supermassive cousins. This is the part of the collision that cannot be solved with pen and paper. It is so violently nonlinear that physicists only cracked it in the mid-2000s using supercomputers to solve Einstein's equations directly, a breakthrough now called the numerical relativity revolution. During this merger phase, the amount of power radiated as gravitational waves is almost incomprehensible. When LIGO detected 2 stellar mass black holes merging in 2015, an event called GW-4, the peak power radiated in gravitational waves alone was estimated to be more than 10 times greater than the combined light output of every star and every galaxy in the observable universe. That was from 2 black holes, only 36 and 29 times the mass of the sun. Scale that up to supermassive black holes billions of times heavier, and the numbers stop being intuitive at all. But none of that energy comes out as light. It comes out as pure ripples in the shape of space-time, squeezing and stretching space itself as they pass through it. If you were floating nearby in a spaceship during the actual merger, You would not see a flash. You would feel your body rhythmically stretched and squeezed in different directions as the gravitational waves pass through you, an effect so extreme near the source that no telescope, only a gravitational wave detector, could register what just happened. Finally comes Act 3, the ring down. The newly formed black hole is not a smooth, perfect sphere right after merging. It is a lopsided, wobbling mess, still carrying the memory of the violent collision that made it. Like a struck bell, it rings down through a series of specific vibration frequencies called quasi-normal modes, radiating away its remaining distortion as gravitational waves until it settles into the smooth, simple shape predicted by general relativity for a spinning black hole. In 2021, researchers analyzing a LIGO and Virgo event called GW190521, one of the most massive binary black hole mergers ever detected, found something remarkable in that ring down. They detected not one but two separate vibration frequencies in the dying remnant, direct evidence that the final black hole really does behave like a bell, producing a chord of overtones exactly as general relativity predicts. It was one of the cleanest confirmations we have that Einstein's century-old equations still hold up in the most extreme gravity we know of. Now here's where the story takes its strangest turn. Gravitational waves do not just carry away energy, they can carry away momentum too, in a specific direction, especially when the two merging black holes have unequal masses or misaligned spins. Because the emission is lopsided, the final black hole gets a recoil kick, like a rocket firing exhaust in one direction, except the exhaust is space-time ripples instead of gas. These kicks are not small. Numerical relativity simulations show that under the right spin configurations, the recoil velocity can reach values up to 5,000 kilometers per second. To put that in perspective, the escape velocity of an entire large galaxy is typically only a few hundred to about 1,000 kilometers per second, sometimes up to 2,000 for the most massive galaxy clusters. A 5,000 kilometer per second kick is fast enough to fling a freshly merged black hole clean out of its host galaxy forever. In 2022, physicists analyzing a real LIGO event called GW2001-29 found the first strong observational evidence of one of these large kicks, estimating a recoil velocity around 1,500 kilometers per second, with a wide margin of uncertainty. That is not enough to escape a big galaxy, but it is more than enough to eject a black hole from a smaller star cluster, and it proved that these kicks are not just a theoretical curiosity, they genuinely happen in nature. A supermassive black hole kicked out of its galaxy at thousands of kilometers per second would be one of the strangest objects in the universe, a wandering black hole still dragging a disk of hot, glowing gas behind it, drifting silently through intergalactic space for the rest of cosmic time, no longer anchored to any galaxy at all. Astronomers have actually gone looking for candidates, unusual quasars offset from the centers of their host galaxies, though confirming a true recoiling black hole from electromagnetic clues alone remains difficult and debated. So does this kind of merger actually happen in the real universe, and can we catch one in the act? The evidence is building. OJ-287, a galaxy about 5 billion light-years away, shows optical outbursts every 12 years that match a model where a smaller black hole punches through the accretion disk of a much larger one, roughly 18 billion solar masses, on an eccentric orbit that is slowly shrinking due to gravitational wave emission. Astronomers have also found dozens of candidate binary supermassive black hole systems hiding inside active galaxies, identified through periodic brightness variations, double radio jets, or in a few rare cases, actual double quasars sitting just thousands of light-years apart caught mid-merger. None of these are close enough to their final plunge for us to detect gravitational waves from them directly, not yet, but they are the smoking gun evidence that these binaries really do form and really do evolve toward collision. In 2023, pulsar timing arrays around the world announced something remarkable. Evidence for a faint constant hum of gravitational waves washing through the galaxy at incredibly low frequencies, detected by measuring tiny timing shifts in the pulses from dozens of rapidly spinning neutron stars. The leading explanation is that this hum is the combined background noise of millions of supermassive black hole binaries merging across the observable universe, all overlapping into one continuous signal too faint and too widespread to pick apart into individual events, at least for now. To actually watch one of these mergers happen in detail in something closer to real time, we need a detector that can pick up much lower frequency gravitational waves than LIGO can, because supermassive black holes ring at a much deeper pitch than stellar mass ones. That is the entire purpose of LISA, the Laser Interferometer Space Antenna, a European Space Agency mission planned to launch around 2035. Using 3 spacecraft, separated by 2.5 million kilometers, flying in formation to measure gravitational waves in space where there is no ground noise to drown out the signal. When LISA finally flies, it should be able to watch the entire in-spiral and merger of supermassive black holes for weeks or months before the collision, not just the final fraction of a second like ground-based detectors see for stellar mass black holes. That means we could get advance warning, point telescopes at the right patch of sky, and potentially watch the electromagnetic afterglow of a supermassive black hole merger unfold in real time. Gas heating up, jets flickering, and possibly a recoiling remnant carrying its disk away afterward. What is left behind in every case is a single black hole that remembers nothing of its two parents except their combined mass, their combined spin, and possibly a very large velocity. No hair, no scars, no history, just a clean, spinning, warped point of no return, quietly settling into the center of whatever galaxy is forming around it, or hurtling off into the dark if the kick was strong enough. Every large galaxy we see today, including our own, likely carries the memory of mergers like this baked into the black hole sitting at its center. And evidence suggests even our Milky Way's Sagittarius A star bears the fingerprints of a past collision roughly 9 billion years ago. In a few billion years, our own black hole and Andromeda's will begin their own version of this dance. And if LISA and its successors are still watching, by the time the next generation of galaxies collide somewhere else in the universe, we may finally see one of these events unfold from start to finish. If you want to be there when that happens, or at least see it explained the moment it does, subscribe, because this story is far from over.